So, any questions about a 6-inch diameter pulley attached to the 1-inch diameter shaft of 2-inch length being supported by the load of supporting load of 2,000 pounds? And we're gonna say that this is. I'm gonna do this problem for finding principal stresses, and I will be using this problem to find torsion and stuff like that. Do I have to go over that as thoroughly as possible? Someone said yes, please. Let's go. We have a first things first. Of course, we want to start with a free body diagram. Well, let's see. This would be probably the motor of my pulley. This would be a 2-inch shaft with a cross-sectional area of but with 1-inch diameter, and a pulley that will be a 6-inch diameter as well. And it's asking us determine the location of the high stresses in 1-inch diameter shaft and calculate the principal stresses at this point. So the actual picture will look something like this. This would be the pulley. And of course, I already messing stuff up. I forgot to add 2,000 pound load right here, which would be, in my case, it will be right here. It will be causing what would be? It would be counterclockwise rotation. This would be the shaft, and this would be the motor. So majority of the stresses are usually as far as possible, okay? And we're gonna have, the way how I think about it is, we're gonna have it right at this red dot. Now, the reason why it's gonna be right at this dot is because we're gonna have shear at that point, and we're gonna bending stress at that point as well. And subsequently, since we have bending moment stress here, we're also gonna have the bending moment stress there down at the bottom, because that's just how the shafts will work, right? It will be shaft. Oops. And it's gonna be looking something like this, where maybe this would be in tension, and then this would be in compression. So I do record this, yes. So if you guys have paid attention in a class, teacher got in quite a bit of an argument with me, saying that we can assume that shear tensile is negligible. That is because the shear tensile is so much smaller than shear torsional, and it would only differ by within the 5% of the calculations. Okay, so those 5% can be dropped down, and that's what exactly allows me to assume that I'm gonna have a maximum stresses at this or this point. Okay, now the way how we usually calculate the torsional shear is gonna be a torsion itself times the distance from the center to the point. Sorry about that. Let me turn this off real quick. And yeah, so the maximum torsion will be happening exactly at the edge of this guy. And they said that it's a solid. Therefore, we don't have to do any weird calculation with the J. And the J is what we're going to divide by. Now, the J is essentially the same thing as inertia, but I would say it's not exactly correlated with the distance away of an object, but more as a distance away inside of the cross-sectional area. So to calculate this, we're going to have to calculate the torsion. And a torsion is just like a moment. If I would take a look at the pulley right here, this is 2,000 pounds, and the distance from here to the center is 3 inches. So my T, capital T, is 2,000 pounds times 3 inches. And the radius from the center of the shaft to the edge of the shaft would be 0.5 inches, because they stated in a problem that I have a 1-inch diameter shaft. And the J. How to calculate the J? The book and a teacher and everybody else would say that the J is just pi over 32 times diameter out square minus diameter inner square. Or I prefer to do it in radiuses, so it's just pi over 2 times r inside, r outside square minus r inside square, because the correlation between the J and I is just J is just a double I. It will be pi over 4 r out square minus r in square. That's just easier for me to remember that I, J, K. So I and J stand next to each other, and I is just double the J. In our case, we don't have our inner diameter. That's a 0. So we can say that we have, I'm just going to combine this together. This would be 6,000 pound inch. Thank you. To the fourth, right? I have totally goofed on that. To the fourth, to the fourth, to the fourth, to the fourth. If you would do a stupid mistake like I did, I hope you all know the units of the stress. It should be a force per length measurement squared. So if you don't end up with a pound per inch square, or newton per meter squared, or newton per millimeter squared, that probably you made a rude mistake forgetting to quadruple instead of square. Okay, so thank you for reminding. That was a lifesaver. 0.5 inches divided by, I'm just gonna go with my notation, and I'm just gonna say it's a pi over 2. The outer radius was 0.5 inch to the fourth, so the 4 cube, and that crosses out, and we left with 2 times 6,000 pound inch divided by pi times 0.5 cube inch cube. Gets us out to 2, crosses out. Take out our trustworthy calculator, and we get 2 times 6,000 divided by pi times 0.5 cube. And I get somewhere about 30,550 7.75 psi. So that is the first thing that we learned how to what to calculate after our first exam, how to calculate a torsional stress. Now, the next step should be all familiar to you, how to calculate the bending stress. And that is just a moment times the radius divided by pi over 4 times the radius to the fourth. Also, if you like to follow book and you don't like radiuses, this should end up being pi over 64 times diameter to the fourth. Now, the moment would be specifically for um, the shaft. It will be 2,000 pounds times 2 inches times 0.5 inch for the radius of the shaft divided by pi over 4 times 0.5 inch to the power of the fourth. You can also plug that into your trustworthy calculator. Just make sure to use parentheses over pi over 4 when you plug in pi over 4 inside of the denominator. I really hate when I calculate stuff and I just do silly mistakes like that, and I'm getting the points deducted from my sloppy work. It's you can sure take screenshots. I usually upload videos the same night as I make them. Granted, this is my only second video, so the regularity of me doing so would be 2 out of 2 if I will succeed. But it should be available online, and I think I did drop the link to my YouTube channel. So please subscribe. And we get 40,743.67 psi. Now, if you don't noticed, we have only one sigma and we have only one tau, and usually our Morse circle comes with two sigmas sometimes, and it comes with pardon me, with a one tau. In this case, the thing that I would be paying most close attention to draw my little square would be actually right this little square up on top of the shaft, inside of not actually inside of the motor. If anything, it will be actually really top part of the shaft itself. And if I blow this up, this would be the guy, and this guy has a shear going like this. Oops, sorry about that. I meant to say like this. And the reason why I picked exactly that top little square up there is because in that point I'm gonna have a tensile stress, as opposed to at the bottom I'm gonna have compressible stress. So if I have tensile stress, I'm gonna have my arrows going out like this. So this guy was what? This guy was 30.6 psi. For those who don't really enjoy dealing with imperial units, just like me, I'm just gonna say that 1 KSI is equals to 1 kilopound square inch, or 1 kpsi. They sometimes write it out the way how I cannot write it out, which is nothing more than 1,000 psi. So I'm just gonna, for the sake of room on the picture, I'm just gonna convert everything to KSI real quick and say that this is 30.6 KSI and this is 40.7 KSI. And all I got to do is just draw my reference. My God, this thing doesn't like me today. There we go. My poorly drawn coordinates for the Morse circle. It's very useful for these guys to use a drawing tablet instead of a pen or pencil or the marker. How our dear Professor loves doing, because you just get to use simple things like circles and straight lines. This would be sigma. This would be a tau. And I'm just gonna say that since I don't have the y stress, I'm gonna say that sigma y is a 0. Sigma s was 40, so somewhere like, how much I have here? Not yet. 40.7 would be somewhere right here for the sigma x, and the tau was 30. So let's see if I had something about like this. What's my tau? Now we do need to find a couple of things. We need to find sigma c, and the sigma c is just sigma x minus sigma y over 2. So in our case, it will be 40.7 divided by 2 will be, give it or take, if I use absolute values on my calculator without rounding, be 20.4, and the radius would be a tau itself. So this guy right here will be my radius. Am I mixing something up, guys, or not? I totally am. I totally am. I totally am mixing something up, because the idea of this is that the shear right here should be the same shear on opposite sides. So 2, 4, 6, 2, 4, 6. And if I use Sharif's method and draw the line from here to here, give it or take, if I would be a little bit more accurate with my drawings, because I didn't put the dot where I was supposed to put it in the first place. This thing would actually go through the sigma. Would go through the sigma c. So this guy right here is your radius. And if you would want to draw a circle, it should start at this point and end up at that point. Let's see if that would be anywhere close. Yes. Now, with that being said, I can find my the principal stresses right here. This would be sigma 1. And then this right here would be my sigma 2. Now, how do I calculate that? Well, the first things first, you probably want to calculate a radius itself. Now, how do I calculate the radius? I would probably use just a Pythagorean theorem and say that this is square root of tau squared plus sigma x minus sigma c squared. Also, I hear a lot of popping happening in general chat. If you guys can tell them to shoot stuff in a study groups chat, that would be awesome. Mm-hmm. I used uh, the diameter of the shaft itself, since I'm being asked to find a high. It says blah blah blah. My bad. Problem asks determine the location of the highest stresses in a 1-inch diameter shaft and calculate the principal stresses at that point. So my whole primary objection was this square. Should probably use other color. That green square right there. Now, if I zoom in on that little green square right there, right here, I'm gonna have a torsional shear going this way, and I'm gonna have a tensile stress right here. So I use the diameter of the shaft itself. Okay. What does he mean when he says? Come again? And and for I, the moment of inertia, I also used a diameter of the shaft because this red guy right here is taken with respect to the fact that you're not gonna have any moments in the middle of the shaft, just like on this diagram right there. That little sigma looking thing is actually my normal stresses to the cross-sectional area due to the bending. Okay. There was a question about what does he mean when he says determine stresses at the angle 30 degrees clockwise from the x-axis. Great question. Let me find my principal stresses, and we will get to that in a moment, because that is actually a good question to ask. What was I doing? I was calculating my radius. It was 30. Oops. It was 36.73 KSI. So then the stress 1 will be sigma c plus radius, and stress 2 will be sigma c minus the radius. So be 20.4 plus 36.73, and then 20.4 minus 36.73. I usually don't erase any numbers in my calculators, so if my decimals would not make sense on the paper, that's because I'm rounding based off what I see on the calculator itself. So I get 57.5 I might as well say it. 1 K KSI, yeah, KPA. And then here we get negative 16.35 KSI. Now, to understand what does he mean when he says determine the stresses at the angle 30 degrees clockwise from the x-axis, let me take a look at that real quick before I BS my way out of it. This was all torsion. It is homesteading, yeah. Double theta. Oh, yes. So this yellow line right here is your x and a y coordinates that correspond to this figure, this being x and this being y. Okay, so if you want to go 30 degrees clockwise off of this guy, well, the first things first, you probably want to know what on earth this double gamma is. Okay, and then 30 degrees in life will be 15 degrees here, so those 30 degrees will be right here, and I'll say that this is what would be, it will be actually, it'll be 60 degrees because we double everything here. So your job in this case is to find what is sigma right here and what is shear right here, right at this point. Okay. Do I need to perform the operation on this and actually go step by step on that as well, or my explanation was more than enough? Okay, cool. So since this guy is a circle, we know that this is the R as well. And the first things first, what I'm gonna do is I'm just gonna try to find that angle over there. That green angle over there. That angle over there made almost no sense. I'm gonna focus on this triangle for that purpose. And the things that I know is I know my R and I know my shear stress. So I'm just gonna say that double gamma, this time it will be a sine inverse of the tau over the radius. Any questions about this? How did I pull this thing out of a hat? Okay. Okay. I'm gonna keep it. Let me draw out this triangle on the side right here. So going around sigma c, this guy would be a radius. Okay, if I follow this green line, that's where my sigma x and my tau meet. Okay, so the distance from the sigma axis down to this point would be equivalent to the tau. Okay, it will be this green dash line right here, and my angle located is exactly at this double gamma here. Okay, if you do trigs, opposite over hypotenuse would be sine. You just take arc sine, and then you divide by 2, you get gamma is equals to arc sine of pi over r over 2. Okay, you don't really have to calculate for gamma itself. Your actual primary objectivity is double gamma, because the next thing you will be after, as a matter of fact, not exactly 60 degrees itself, but you will be mostly focusing on this angle right here, because this angle will make another a triangle that you will be focusing on as well, and it will be this guy right here. Okay, this distance right here will be your new shear, and then this value right there will be your new sigma. Okay, no, so there will not be principles. So we are way past the point where we're finding principles. Those principles are right here. No, he wants specifically, yeah. He wants specifically a shear, and specifically um, bending or normal mass stress. If you take this figure and Lord have mercy, to rotate it exactly 60 degrees, it will be if you rotate this figure something like this. I should drop out of engineering school and become an art guy, because these lines are looking curvy flat tonight. There you go. So at this point, you want to find out what will be your I'm gonna use blue. What will be your shear right here, and what will be your normal right here, where this is uh actually 30 degrees. I drew it a little bit off. It should be 30 degrees, not 60. It's 60 on Moore's circle because we double everything, but it is normal on a figure itself. Hope that made sense. Someone is asking that they use tangent inverse as opposed to sine inverse. I used tangent, or my bad. I used sine because I just can use only two of variables that I already have stored in my calculator. I don't have to go back and look at this triangle and say that, well, this distance right here will be sigma x minus sigma c, and I will kind of eliminate the possibility of making an error, because the exam I will be taking will be around 11 a.m. and I am the guy who wakes up literally, if not in the middle of the exam, I wake up like 5 minutes before. But if you would do tangent inverse, you'd be looking at something like 2 gamma tangent inverse opposite over adjacent would be tau over sigma x minus sigma c. And yes, it is a preference. You can choose whatever one you would like to do. Cool. Do I have to actually crunch numbers in this, or the idea how far physically I've gone is enough? I'm just gonna make a point that let's call this guy alpha. That guy alpha that you will be working with will be 180 minus 60 minus 2 gamma. And then you would have a new triangle. I'm gonna make it a little bit smaller so I could fit it in. This would be alpha. This would be the radius. Knowing alpha and knowing a radius, you can find your tau. This guy would be sigma c minus sigma n. And then from there you can find your sigma n. Let's call this guy sigma n. Got a wee bit quiet. Okay. Well, should I keep going with this, or this is more than enough? Okay. Well, at this point, all you gotta do is just crunching of numbers. Okay. Um, let's say I'm gonna stick with the double gamma as opposed to just the gamma. So I'm gonna bypass this guy. Um, alpha would equal to 60. My bad. 180 minus 60 minus sine inverse of my tau was what was my tau? My tau was 30.6 ksi. And then the R is 36.73 ksi. And if you plug that into your calculator, you get somewhere about 63.69 nice degrees. So now you can actually look at this triangle right here, and all you need is a little bit of trick. You can say that tau nu, since this is opposite over hypotenuse and that's your angle, tau nu will be radius times sine the alpha. And that would be that would be 32.92 ksi. Then your sigma n is gonna equal to uh, well, let's see. Let's start with the baby steps. Your sigma c minus sigma n is gonna equal to r cosine alpha. So then your sigma n is equals to sigma c minus r cosine alpha, which in our case, sigma c was 20.4 psi. And we get very small, just like I predicted by my picture. The value we get 4.1 psi. Okay, so at this position, if you rotate this thing 30 degrees, your sigma x will be 4.1 psi, and your shear will be equivalent to 32.92 psi. Okay. Okay, so not as much of actual engineering and physics concepts, but more of a trigonometry and stuff. Okay. Do I need to answer any more questions about what did I say? I thought I said it is r cosine. It is r sine for the shear, but it would be cosine for the sigma n because this is adjacent and hypotenuse. BP1 had r cosine. Right. Homework 7 for BP1 he did r cosine. To find what? So the way how he did is I can bet you that me and him got the same results. And the reason why he did sine is because he called his angle right here, where I called my angle by the sigma axis. Okay. Yeah. Okay. And it's a lot easier and nicer to work in my opinion over the straight line because you know what the angles add up on a straight line to. It's just 180. Okay. Cool. 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 Any more questions on this? Comment once. Comment twice. All right. Next problem it is. Let's see. Oh, as a matter of fact, I actually had that problem queued for the next one. I guess we can skip it. Let's take a look at this guy then. And I bet you this guy took a lot of people for a loop. It says A wire hook is loaded with a force of 2,000 pounds. The hook has a wire diameter of 1 inch, diameter of 3 inches, and a central distance between the eyes is 10 inches. Determine the inner and other stresses of the loop where bending moment is the maximum. So there are a few ways you can um, I guess kind of draw it. The way how I did it is I drew it like this. I literally made an S out of it. Not exactly how I had it, because I actually used my time in a circles to draw it out. But the idea was like this, where I'm just gonna call this free body diagram. This distance right here was 10 inches. The eye diameter was 3 inches, and the wire diameter itself right here was 1 inch. Meanwhile, everyone writes it down. I will make sure that I will find exactly what I need. Y'all remember, right, that the exam is open book, and you can actually use your notes on a piece of paper or whatever to solve your problem, right? Huh? Oh, I am being recorded right now, and the teacher does watch the videos. I cannot give you answer on this. I am so sorry. That is something you may ask me later on and see if I really willing to sabotage my educational career, or maybe a button of the classmates would be generous enough to do the same thing. So with these guys, we do need to acknowledge a couple of things. That yes, we will still be using a bending moment equation, but it's gonna be a little bit more complex than one would like it to be. So I'm gonna draw a cross-sectional area of the wire. And I'm just gonna say that this right here is the common axis. Somewhere right here will be the neutral axis over here. I probably should do it in red. And oops, I might as well redraw it. A little bit bigger. So the common axis that we used to see, and then the actual common axis that we are experiencing at this point, because we are being curved. We're not being right in the middle like the straight beam would be like. Okay, for that guy, you'll be straight or right in the middle. So there are a couple of things we need to acknowledge. First things first, we need to acknowledge that there's another thing called a radius of an eye. And I'm pretty sure I called that radius of an eye. This actually should have been 3, like this. I'm pretty sure I called it up to the neutral axis as we used to see it. There's the outer radius right here, and there's the inner radius right here. Okay, and then there's a little pipsqueak E right here, and then we're gonna essentially measure things off of this guy. So we're gonna have the CI going right here, and then CO going right here. A few equations to remember, and those are the things that I will, like, hands up, gonna say that we haven't done many problems with that. Fingers crossed we're not gonna have this on exam, but for the sake of my consciousness and me not falling into another loop-to-loop of unknown questions, I am honestly gonna write it down on a piece of paper. And those equations are, to calculate E, it would be just RC minus A over integral of dA over R. Now, this looks quite complex, and if I remember, our beloved professor posted a handout in our Canvas, curved beams. And that is this thing right here. I hope you all can see it. And oh my god, this is tiny. Here, I think this should be helpful. You can just honestly go to the canvas and open up for your own use, and literally use that to calculate everything you guys need at this point. I'm just gonna follow along the equations. Capital R, which was my RC or RO, no, RC on the picture, yes, plus diameter over 2, so that was 1.5 inch plus 0.5 inch gives me 2 inches. Or I would assume this is Rn. Yeah, Rn. Radius to the neutral would be 4 times 2 times R minus square root of 4 R squared minus D squared at the bottom, and then D squared, so that would be 1 inch squared divided by 4 times 2 times 1.5 inch minus square root of 4 times 1.5 inch squared minus 2 minus 1 inch squared. I get somewhere about 1.46 inches. And now, instead of calculating all of that, E is equals to, what was it, R c minus integral of a over integral of dA over r. I can just take a look at the picture and see that E, that little pipsqueak E, is just a difference between RC and the RN. And I'm gonna simplify my life by doing that and not even bother getting my hands dirty with the calculus that I'm not ready to do at 9 p.m. And I get 0.54 inches. Now, the reason why I to need to do all of that is for me to calculate the sigma inner, I need moment divided by E times the area multiplied by Ci minus Ri. And then to calculate my moment other, since this guy, we know that guy will be in, it turns out this will be positive, and the other end needs to be in compression to accommodate other to be in tension. This guy would be negative m over ei, ea times co over ro. Okay, the moment is a moment. It would be those 2,000 pounds applied right here off of the distance right here, and I think I'm gonna have to calculate that the distance away from the this green line right here. So that would be a radius of the eye plus half of the thickness of the wire. So that's 1.5 and 0.5. And that would be 2,000 pounds, I said? Right? Right. 2,000 pounds times 1.5 inch plus 0.5 inch divided by 0.54 inch. And the area is the area of the wire, so that should be pi times 0.5 inch squared. And then Ci, as I drew, was the distance from the Ri minus E. So you can say that it's 0.54 minus, if this is 1.5, this is 0.5, so it's 1. Hold up a second. Oh, it's the Rn minus Ri. My bad. Right? Right. It is Rn minus Ri. I am so sorry. And my Rn was 1.46 minus 1 divided by Ri, which is 1. £2,000 times 0.5, 0.5, that should be 2. That's squiggly came out bad. So I come up somewhere about to be 536 psi, and then here I'm gonna have almost the same scenario. Oh, oops! What happened? It should have been times. See, the more the numbers you crunch in within one equation, the more mistakes you get to make. That sounds a lot better to me. I was about to say 2,000 pounds cannot give me a quarter of this stress. It should be 8576.37 psi. And then this guy would be the same story, but I need to find my CO, and a CO will be negative 2,000 times 2 times 1.5 plus I heard a comment. Mm-hmm. Uh so we are doing sigma and sigma O, but it's not exactly F over A. No, this is no. So if you actually zoom in onto a hook, so let me actually draw it out right here. Okay. And let me compare. So that's a hook, and let's say we have a weight right here. Okay. If I compare that to the regular beam, also let's say for this simplicity to compare, is going to be circular too, right? And now since the beam is straight, I'm gonna have my sigmas being done like this, and they will be done right at the middle of the sectional area. Okay, and this is what allows us to say that sigma is equals to the moment times distance away divided by inertia. Okay, this is what we know from the last time, but this time our picture itself will be a little bit more complex, because let's say this right here is the center of the a wire right here, but the bending itself is not going to be done exactly at the center of the wire. It will be done a little bit closer to the inner radius. It will be done somewhere right here, and it would most likely be done somewhere where the moment applied being a maximum, which is right in this cross-sectional area. Okay, and the picture for that being done is gonna be looking not exactly straight lines like we used to be right here, right? It'll be done by curvilinear like this. Okay, and that's why we need to go through those extra steps to find our sigmas. It is still, if you will come and take a closer, it's still moment over the area. Okay, but the thing is that uh, you're being shifted away from your axis. That's where the E comes into to play, and your distance over what you are applying a force is also a little bit shifted. Okay, and I also realized that that is not 2, that is just a pound. My scribbles are getting worse and worse on me. Okay, I hope I answered the question on this one. Okay, so that should be divided by 2. So we get 4288.18 psi. And then here I'm gonna be dealing with a CO and CI, and a CO is the radius O minus Rn. So the radius O is be 1.5 plus 0.5, so that would be 2. 2 minus 1.46, and the RO will be 2. And I get negative 2546.48 psi. Okay, so from here, first things first that I would advise you guys to do is to take a look at this PDF file that I dropped to you guys in the chat, and don't waste time on doing unnecessary stuff. So there's no axial stress. There is axial stress, of course, yes, but I would argue just how Professor argued last time about that translational shear is negligible compared to the torsional shear. We don't need to worry about that. But if you do want to include it in and be more precise, I mean, by all means, sure, please do that. You will actually have a higher opportunity of getting better job than any of us because you are thinking outside of the box and you're getting stuff done right. I don't believe if he actually asked us to include it in or not. Yeah, he did. He did, or at least I did in my calculations. I did add that to my I did add that to my thing. Yes, I did add 2,000 pounds over by over times over 1 inch. Yes. All right. Any questions about curved moments? So sigma I and sigma O are the sigma on the inner part that is happening. Oh, Ci and Co. Ci and Co are just the distances to the edge of the wire from your new neutral axis. Okay, so before in a straight beam, our CI and CO will be the same. There will be this distance and this distance right here. And since we got right in the middle, there will be identical. In our case, since we are working with the bend stuff, we're gonna have a little bit of a shift where our neutral axis would be actually right here. So our CI would be distance from the neutral axis to the inner edge, and CO would be distance from the neutral axis to the outer edge. So what are possible questions? So first of all, that image was not posted. I have a feeling he just doesn't know how the canvas works. I would prefer to set those questions after the session, if that is possible. Any questions on more questions on the bent moments? Comment once, comment twice. I guess not. All right, moving on. How about do you guys feel on the bended shafts that are being applied by the forces straight into it? So things like Johnson column and Euler column. We got a lot of people, and a lot of people are not typing, not chatting, nothing. Some may have trouble on it to use Euler and Johnson. Kinda. Okay, so 421. Do you remember what homework this is? Is it 7? 321 BP2. 321 or 421? 421. Uh, sure, I can explain that. I didn't draw shears a circle on it because I just got used to the um, equations. Do you mind if I actually get back to that after? I will do 449. So do 421. Okay. So let me just say that there is one assumption that we have to do, and that assumption is we need to decide which equations, which constants we gonna use for this problem. There are a few options. There is I think theoretical. There is AISC, and then there is the third one that was he said to use theoretical, even though the problem was not using theory. Okay, we will use theoretical values. So let's start with the A. It is a boundary condition pinned. And if professor said to use theoretical, we will use theoretical. Pinned theoretical said that assume LEFF is just equals to L. Okay, you can write down a table. I'll just say table 4.4. Okay, so before I get to anything like this, if you remember the graph, there is this kind of looking graph that splits right in the middle, and it splits it onto Johnson column. Let me not butcher poor guy's name and actually spell it out right. And then anything past this would be Euler number. Euler column. So what is the magical value that sets the two apart? Well, there is a magical value called SRD that equals to pi square root of 2 Euler's number from the table divided by SY. Okay, and if you are below that number, you are Johnson, and if you are greater than, then you're Euler. Okay, so first things first, I'm probably gonna drop down the free body diagram. Okay, such that the outside was a 4 millimeters, and the inside was 3 millimeters. Okay, so SY I believe was, yeah, given to us. Cool. So let's calculate this guy real quick. It says use SY of 1500 megapascal and 300 megapascal for the steel. Condition pinned, and I believe this was a steel bar. So you're gonna go pi square root of 2 Euler number. I'm gonna have to look it up. I just have my notes open in front of me. I'm just gonna drop that this is 206.8 times 10 to the 3 megapascals. They give it in a gigapascal. I right off the bat convert it to the megapascals because the units just nicely cross out. And I get my value of 116.65. Now, the thing that I am going to be converted into is comparing it to is the SR, and the SR is EFF divided by the K. Now, the K is square root of inertia over cross-sectional area. So for the square, especially the the the, the, the hollow one. We're gonna be doing it around the middle axis, around the pin. The inertia total is gonna equal to inertia of the outer minus inertia of the inner. And since they're both squares, I can factor it out. I can factor out 1/12. For a rectangle is height times the base, but since they're all the same, it's just gonna be a to the fourth minus a outer to the fourth, a inner to the fourth. Gives me 1/12 of 4 millimeter to the fourth minus 3 millimeter to the fourth. And I get, actually I could have not calculated it that and kept it with the equation, but since I have done this, I might as well finish it. And I get 14.58 millimeters to the fourth. And area will be cross-sectional area. It will be area outside minus area inside. It will be 4 millimeters squared minus 3 millimeters squared. 16 minus 9 will be 7 millimeters squared. So we get 14.58 millimeters to the fourth divided by 7 millimeters squared. Square root of that. Will be 1.44 millimeters. Cool. So then my SR is equal to, since my assumption is theoretical and my LEFF is equal to L, and the length is 100, it will be 100 millimeters divided by 1.44 millimeters will be 69.28, and this is way lower than my SRD, right? Therefore, this is a Johnson column. Okay, and then a problem asked to do the same thing for any other conditions. You just pick whatever assumption you need to make, and you calculate SRD. You calculate, well, SRD would be the same for everything. The only things that will be changing will be SR, and you just compare that to the SRD, and then you make your definition. Now I remember problem was asking specifically something else. It says define if Johnson Euler column and find the critical load. Now how do we find the critical load? The critical load can be found by, I'm gonna call it a P. Be found as an area multiplied by the SY minus 1/E times SY times SR divided by 2 pi everything squared. Okay, Our area comes out to be 7 millimeters squared. SY was 300 megapascal minus E was 206.8 times 10 to the 3 megapascal times 3000 megapascal times 69.28 megapascal divided by 2 pi squared, and that should someone come out to be 1.73 kilonewtons, which means this is the maximum load the column can handle before it's gonna start crippling. Any questions about how to do this? And should I do one more with other condition? I guess not. Well, well. And that being said, I'm gonna do a homie in favor and do 421. Oops. Drop this right here. Okay, so figure shows on a mobile wheel with the two columns, styles of lug wrench being used to that in wheel nuts is single ended wrench in A, and the double ended wrench in B. For each case, two hands are required to provide forces respectively at A and B shown. The distance between A and B is 1 foot in both cases, and the handle is diameter of this much. The wheel nuts require torque of 700 foot-pound. Find the maximum principal stress and the maximum deflection of each design. I remember this problem, and I remember having a problem with that. And the problem is that they didn't include the size of the thing that goes into the wheel, which was very important. And I'm just gonna add it right here. That this distance right here is also 3 inches. Because the idea behind that is when you apply the bending moment, and especially if you're trying to calculate a displacement of the handle, your handle will not only bend this way, but it will also try and bend this way as well. Okay, so you will have this change in Y right here. You'll have this change in Y right here as well. So in total, you will be dropping down about this much. Okay. So do I need to explain which concept is better and which one is not? Yeah. Okay. Mm-hmm. Yes. Let me just reread the problem again. You will have to use both. Yes. Let me put an A in here. So free body diagram. let's say this is the log right here, and this is the handle. You will have to use both the 3 inches right here and 12 inches right here as well. Okay, so for the, and that is only for this sigma. So for the torsion, you'll just stick with a T R over J, assuming that T the tensile is way less than T torsional. So you can neglect that. But for the sigma, it's gonna be a moment of the, I'm gonna put it as a log. Huh? It's gonna be both. It's gonna be a moment of the log times the radius of inertia plus the moment of the handle times the radius over inertia. Right? That's what I said in homework. Find a maximum principal stress and a principal deflection. Uh Actually, for the sigma x, you don't need. Yes, of course, me being dumb dumb. Uh, you don't need to use 3 inches because your the force is being applied right here. Okay, so what you are gonna need to do, you will need to use both ends to find your delta y. Okay. So for this one, sigma x is only this. And then for the delta y, you will have to include delta y for the socket plus delta y for the handle. Right? Otherwise, it just doesn't make any sense that this thing would not bend. Even if you try, I don't know, it's too far. Oh, even better. If you try and hold by this guy right here, okay, you will start applying force, and of course you will cause not only this motion right here, but you will also cause this motion right here as well. So it's gonna go like this. You can see it. It will be in a video. Please follow through. I think you will get the idea of what I was I was showing. Okay. All right. Any questions on that matter? Anybody else? Keep in mind that this will be a very interesting video to watch because it captures only my voice. So you will have like a solid 10-minute talk of me with myself. for 421, I got for the of stresses, we got sigma 1 being 1753 and sigma 2 being 0, and the torsional would be 1753 for one of them, and then for the other one it would be 3505 and 0. I'm trying to remember, why did I get two separate things? That's just for the A though. I think it's because it's only one hand does it, so yeah. Okay, and then for the B, I got 1752 and a 0. I imagined it in my head. He didn't take off points. I was happy with that. Okay. I didn't use more circle because I had a great imagination. Okay. Can we? I would be happy to answer your questions on homework after I will finish this video. Okay. Okay. All right. Cool. Where were we? We were actually a few problems away. Let's take a look at the cantilever beam supported in the middle and loaded at the end. I think this guy will be awesome to cover. So let's start with a free body diagram. Whoever is not muted, please unmute them with themselves. Thank you. Gonna start with a free body diagram of a beam being supported in the middle with a length of L. It is being supported right in the middle, and the force will be going straight down right here. I honestly, this guy, I prefer to go with the singularity of functions, just because I prefer them more than anything else, because they make more sense to me, and I think they will be useful to review for you as well again. So we're gonna start with the V sub x, and I'm gonna start drawing from right to left, and the idea behind that is that I will not have moments when I will be looking for the constants. Okay, so now we still have to find C3 and C4 if it is applicable, but when you are gonna get to the L's and whatnot, you're gonna come to things like L minus L to some power of A, and 0 to any power is just 0. Okay, so that's the idea why I prefer going off of a free end. Okay, so starting right here, just right, of course. Just always the finding of the constants, so you don't forget and mess up. Yes, every time you get there, just even if you do shears in the moments, I would advise to put in constants and then prove yourself that they are equal to 0. For example, I'm gonna have I'm gonna start with actually loads in that case. Q of x is equals to negative f at x minus 0 to the negative 1. I forgot the result. No way. RA straight in the middle. RA at x minus L over 2 also to the negative 1 plus Ry x minus L to the negative 1. And then this guy makes a frowny face like this, so my moment is negative. Minus moment x minus L to the negative 2. Now if I integrate all of them, like singularity functions work, you get negative f x minus 0 to the 0 plus Ra x minus L over 2 to the 0 plus Ry x minus L to the 0 minus m x minus L to the negative 1 plus C1. Okay? Here is the point where you have to convince yourself that the C1 is equals to 0. And the way how you can do that is let's come up with the L plus. So such that L is equals to L plus tiny little L, where delta L is approximately 0. Okay? So what this allows me to do is that it allows me to say that V of L plus is equals to 0. And I have, because there are no other forces being applied on it besides those that are on my free body diagram. 0 is equals to negative F plus Ra plus Ry plus C1. And since there is no other force here, my C1 equals to 0. So that guy is just gone. And if I integrate this again by the method of singularity functions, I get f of x minus 0 to the 1 plus Ra x minus L over 2 to the 1 plus Ry x minus L to the 1 minus m x minus L to the 0 plus C2. And then you do the same thing. You just say that m of L plus equals to 0. And we have 0 is equals to negative f times L plus Ra times L over 2 plus Ry times 0 minus m plus C2. Well, we do have, if I go at L plus, I end up somewhere within this region right here. Okay, within this region, if I go off of my length, I do have negative F times L that causes a rotation. I do have negative RA, oh, that should be plus sign, that causes counterclockwise rotation. My Ry is right at the 0 and it's gone. And then my My also causes rotation. So there's nothing else except there's nothing else except those two. So my C2 also equals to 0. This guy can be also rewritten as a EI y double prime of x. I'm just gonna clean it up a little bit. my. Yes, it's going to be my. Y. In order to not lose yourself, make sure to use the actual variables that you do have in equations. And now, if I integrate this again, I'm going to get EI theta x is equals to negative f over 2 x minus 0 to the 2 plus RA over 2 x minus L over 2 squared plus RY over 2 x minus L squared minus my x minus L to the first plus C2. Drop it in the chat. C2 is 0 or not? And what's your reasoning behind that? I feel like that came out. Hi kids, can you guess an answer? And then silence, just dead silence. Okay, so we have a couple of guesses. We have not 0, but I forgot the reason why. Fair reason. It is Sunday, 10 p.m. I actually should be having my second beer and watch anime with my girl and enjoy my night. And then there's another says 0 because x at 0 is 0, therefore the theta is also 0. But if you pay close attention to where my x is located, and it is located, I'm gonna pick the blue color right here. Right at this point, there is no way that my angle of deflection will be 0 because this guy will be sagging like no other. However, there is a place where my angle will be 0, and that is right by the wall. So actually, it'll be at x of L. So when theta L equals to 0. So then EI times 0 is just 0. I can ignore those. Someone actually did ask professor in the class, can we just ignore EI? I'm like, depends on what you're trying to do. Minus RA over 2 L over 2 squared. L minus L squared is 0, and then M y times L minus L is also 0, so that's gone. So all I have is just C3. And this is exactly what I meant, why I like putting my origin at a free end. Is because my moments that are being applied by other forces or other objects, they will be gone. Someone said yes, plus array. Thank you very much. Yes, plus array. And guess what? Our C3 is not a 0. Our C3 is FL squared over 2 minus, this time minus array. This time it's minus array. And it's going to be 8. And then we keep on going. EI y of x f over 6 x minus 0 cube plus RA over 6 x minus L over 2 cube plus RY over 6 x minus L cube minus my, oops, my over 2 this time. My over 2 x minus L to the second plus, I should call that C3, plus FL over 2, FL squared over 2 minus RAL squared over 8 x plus C4. C4 will be 0 or not? Okay, I got 2 no's. Can we go more? Can we be any more confident, guys? Okay, I will take 2 no and that's silence as an answer. It's fine. It's fine. It's fine. But then here's a question on 2 meals. Are we which of these 2 points are we actually gonna use for C4 to find a C4? Is it L or is it L over 2, and what's the idea behind that? So I got an L. Use L for C4, I know, but why? Just cause, sure, just cause, fine. Let's go just cause. Uh, but deflection is 0 at L over 2 as well, because there's that little guy there at either one. A fair point. Remember, he said to use an additional beam only for your other equation. You can't do that. Nothing stops you to do either. Actually, that was my whole hint. You can't do either. My whole thing of that is that if I plug in L over 2, I have only one additional variable at that point. That's it. So, but the majority said L. Majority rules, fine. I get it. I get it. Majority rules. I'm going to say 0 is equals to negative f over 6 times L cubed plus RA over 6 times L over 2 cubed. 0 plus FL cubed over 2 minus RA L cubed over 8 plus C4. Okay. All I gotta do is just combine of like terms and move everything on the other side. And I'm just gonna do myself a favor and combine these 2 terms together, and then these 2 terms together. And I'm gonna do it with the opposite signs because why not? So we get 1 over 6 minus 1/2. Yeah, it technically doesn't matter because you will not be wrong. if I would have used L over 2, I would actually have only f negative f over 6 times L over 2 cubed to carry as a constant in this case. And then I would have to go with my C3 and C4 found. I would have to plug in L instead of L over 2 as my third one to find what of my resultant forces. Oh my god, hiccups are such a pain. So I get C4 is equals to negative FL cubed over 3. And then I get negative 1 over 6 times 1 over 2 cube plus 1 over 8. And I'm gonna convert that to the fraction. And I get plus 5 over 48 RAL cube. So my whole equation comes up to be EI y of x is equals to negative f over 6 x minus 0 cube plus RA over 6 x minus L over 2 cube plus RY over 6 times x minus L over cube minus moment y over 2 x minus L squared plus FL squared over 2 minus RAL squared over 8 times x plus 5 over 48 RAL cube minus FL cube over 3. Okay, quite a quite a mouthful, huh? So then another place where my y is going to be 0 is L over 2 equals to 0. And I'm going to use that to find the result, and I guess my result then will be RA that I'm going to find first, since all my constants were in terms of it as well. I'm going to get negative F over 6 L over 2 cube, and that all I could have as a C2 as a matter of guys. That could be it. Because RA over 6 is 0, RY is 0, moment is 0, plus FL squared over 2 minus RAL squared over 8 times L over 2 plus 5 over 48 RAL cube minus FL cube over 3. Let's distribute as much as possible before we go any more berserk. I'm gonna get 0 is equals to negative FL cube over 2 times 2 to the 3 is 8. 8 times 6 is 48. Plus FL cube over 4 minus RAL cube over 16 plus 5 over 48 RAL cube minus FL over 3 cube. Okay? All of the L's can cross out. If I'll be very careful, and I will combine all of these guys together as a one fraction, and then all of these guys together as another fraction. You know that feeling when you know you did it right once from the second try, then you gotta show it on public because people think you're smart, and then you just mess up. Should be -5. -5 over 48. F? I use green, right? Yeah, I use green. And then, what do I need to do? I need to multiply that by 3. So, -3 plus 5, I get 2. So I get plus 2 over 48 RA. 48 and 48 can cross out. Therefore, RA is equals to 5 halves F. Can I be possible? Can I get my RA being 5 halves of F? Or people got other values for array? It shouldn't really matter as much. Mm-hmm. Mm-hmm. Okay, so I did get 5 halves. So I did get 5 halves in a homework as well. Someone got 5 halves as well. So we are golden. Sweet. Since we know this, we can go straight to our shear equation. Yeah, in case of mine is alright, yes. So then we can go to our shear equation, and we can say V of L is equals to negative F plus 5 halves F plus Ry equals to 0. Actually, L plus to make that straightforward, yes. And just, send it. Ry is equals to F minus 5 halves F, and that should be negative 3 halves. For this guy. Is that what I got? Yep, that is what I got as well. And then for the moment, it will be just moment at L is equals to negative F times L plus 5 halves F times L over 2 minus 3 halves F times 0 minus M. And that all equals to 0. So then M is equals to 5 halves, 5 fourths, FL minus FL should be FL over 4. Yes. Isn't this tedious? Any questions about any of my steps? Why did I do what, and what's the point of it all? I guess not. How do people feel staying up for more problems? Or should we call it? Drop it in the chat, drop it in the chat. People said keep going. Show must go on. Alright, let's keep going. Let's see, what do I have backed? Should I do pressure stresses in our vessels? You guys understand those, or or not, or yes or not? Mm-hmm. Where to? Oh no, they found me. Pressure. Sure, let's go. Pressure. Principal stress and pressure get the people. Pressure will get you, especially when it's in your blood vessel, man. You know, just a little bit of over, and your vessel pops, and you go poof. It's one of those. I know. I went a wee bit dark over there all of a sudden. Now, pressure would be something that I would also add to my cheat sheet because we had only few problems on them, and as a matter of fact, yes, they did require us to use principal stresses. Good. We will do the principal stresses on those. Now, if only this textbook actually had everything structured, so I would not have to jump from the page to page. Ah, there it is. Cool. So, a 10 millimeter inner diameter steel tube carries a liquid of 7 megapascal. Determine the principal stresses at the wall if the thickness a 1 millimeter, b 5 millimeters. So first things first, you probably want to do is to check if it's a thin wall. If it's a thin wall, oh my god, your life is easy breezy. If the thickness is less than 10 over radius. So I usually call this a ratio of the thickness to the inner radius. And in our case, it comes out to be 1 over 5, which is 0.2, which is bigger than 0.1. Unfortunately, it's not thin, right? It's a thick boy. which means we're just gonna have to bite the bullet and deal with a lot, more of variables that we would like to deal with. There is one assumption we have to do. Assume that it is an open-ended pipe. Okay, if that is the case, then our sigma A is equals to 0. Easy enough, huh? We found none of our sigmas. But here's just a question: what does sigma A means in itself? Well, if I draw a free body diagram of a vessel, opened, closed, doesn't really matter for the time being. And let's say I take a focus on one little segment of the pipe. That segment will be right here, about this big, and it's as thick as the pipe, like that. Okay. All three sides that I drew, they all gonna be subjected to stresses, whether they want it or not. The stresses that go this way are those sigma A's. Okay, as your the vessel close, it boils up. It wants to expand in every single way possible, including the longitudinal way. But if it's open, it'll just go. And not cause any stresses in this way at all. Okay, there are also stresses radial, and there are stresses tangential. So the ones that are tangential are these forces right here. I actually should have drawn it as perpendicular as possible. Sigma t, and there are also radial stresses, the ones that are coming out perpendicular to this, and I'm going to call them sigma r. Now, since the problem is asking us to find a principal stresses, notice how there is no torsion in it. It's all tensile and compressible stresses. Since my sigma A is 0, I'm gonna be focusing on, let's say I'm gonna be focusing on this side right here. Oh, that's a bad color for that. This side right here. So what is happening in that little segment? That little segment is going to be looking something like this, where I believe I usually draw my sigma t's this way, sigma t this way, and then sigma r's are the ones that are going this way. Okay, so that will come handy to us when we will be finding our principal stresses. How do we find stresses themselves? Well, if its external pressure is 0 and we don't know our pressure outside, we can use equations 448 A and B. And those equations dictate that sigma t is equals to Ri squared Pi all over Rho squared minus Ri. squared multiplied by 1 plus RO squared over RI squared. Now, what is RO? RO, I'm going to call it outer diameter. It's going to be ID plus double the thickness. Or outer radius is going to be radius inner plus the thickness. Okay? Nothing more to it. If I draw it out, RO, RI, and a thickness. We get to simply plug in our values inside, and we get the inner diameter was 10 millimeters, so it's going to be 5 millimeters squared. The pressure inside of the vessel was 7 megapascal. Divided by the thickness was 1 millimeter, so that is 6 millimeters squared minus 5 millimeters squared. 1 plus 6 millimeters over 5 millimeters all squared. Let the machine do the job for you. 5 squared times 7 divided by 6 squared minus 5 squared times 1 plus 6 over 5 squared. Where does 6 come from? 6 come from, this is your outer radius, RO. Your inner radius was 5 millimeters, and for this case our thickness was 1 millimeter. 5 plus 1 gives you 6 millimeters. That comes up to be, gonna move this right here, too far. That comes up to be 38.82 megapascal. Okay. The sigma R dictated by 448b is going to be Ri squared pi over, oh, wait a second, Ro, this is not Ri, this is just an R. Now what did I choose for my R? It should be, I think I picked Ri. That's why I didn't do anything about it. Yes, I picked Ri. That's why I accidentally put Ri. So R right here is actually any radius within a thickness you get to pick. Okay, but now since I'm looking for the maximum possible, I want to have I want to work with Ri. Okay. Then the same thing happens right here. 6 millimeters squared minus 5 millimeters squared times 1 minus this time. Six millimeters over 5 millimeters squared. Whoever is unmuted, please do people a favor and unmute. You get negative 7 megapascal. That's what we got. That is what we got. Exactly. So how does this affect us? Well, we don't have any torsion. Okay, so if I do grab this guy, really doesn't like me. And let's say this guy right here is sigma y. And say this guy right here is the sigma y. Huh. Sigma r. My bad. And this guy will be sigma t. The circle would fall right in between them. Like so. With the radius being, with the diameter being the distance right between them. And those two guys are going to be my principal stresses. So my sigma 1 comes out to be sigma t is up to be 38.82 megapascal. And my sigma 2 is equals to sigma r is equals to negative 7 megapascal. Okay? And now let's take a look at if there are no any more questions on this. I would love to take a look at another pressure vessel problem that deals with the same thing, but it's a different case scenario. Okay, and that is next problem 442. What if there is also an axle? And that is exactly the problem. So, or all three stresses. Good questions. Um, you, the way how you've been, I hate that this is being recorded. With my face on a camera too, that's why you guys can see me like it will be on a video. I'm gonna shoot myself. The way how we've been educated, uh, you will have to break it up into three squares. Okay, so let's say I'm gonna be dealing with all three of them. One, two, and a three. You will have to take a look at each one of them separately, where you would have a square. Let's say I'm gonna have a blue stress and a red stress, and then let's say I'm gonna have, actually, as a matter of fact, let me finish this and I will we'll show you that. But we actually have two more circles inside of that circle, how the book has it in the first place. Okay, so then that's one thing. That's another thing. And then that would be another thing, like this. Okay, so you will have to draw all three individual circles for them. You can fit them in on one graph, and as a matter of fact, if I will take a look right here, which one of them I did not have? I did not have axle. Okay, so let's say the red was the axle. Okay, in this guy right here, oh, I should use the other color. In this guy right here, the red one was a 0 and a y1 was the tangent, was the radial. Okay, so let's say this guy is sigma r, and this guy is sigma a, and then this guy is sigma r, this guy is sigma t, and then sigma t, and then actually I'm gonna rotate them places because actually it doesn't matter. It really doesn't matter because the numbers will play out exactly how we need them to be, with our help or without our help. So let's say this is the case, and let's say this is it is actually the case for the problem we have. What is actually happening is let's go this case 1, case 2, and case 3. So this big red circle right here is the case 1. The radial and axial is the case 2. They will fit in right in here. This is the case 2. Then case 3 with tangential and axial, that guy will fit in right. Oh, that's a poorly looking circle. Gee. No better, but I will sleep tonight. That is the case 3. That is because I am technically still having that one stress right here, that sigma a. Okay? Did that answer the question? And that's why you saw this weird 3 circles combined in one in a book. So it'll be sigma 1, sigma 2, sigma 3 is that same one. Yeah, sure. Yes. Uh the way how you define sigma 1, sigma 2, sigma 3 really depends on how you define it on a picture. So as far as you being consistent with them, the notations are just the notations. Okay, if you say in your work that sigma 1 is sigma tangential, and you put it on a graph like this, then you're good. But if you draw on circle one thing, but in your notes you say other thing, it's like saying I have negative moment when it goes counterclockwise, so I'm gonna flip it and forget to change the sign. And yes, this problem was an open vessel, so we had sigma a equals 0. Sure. If you take a look at the problem, or if you even try to blow up a balloon, you'll see that there are no, in a way how the problem described, there are no forces that causing any torsional motion like so. Okay, but as soon as you will rotate it 30 degrees or 60 degrees, how we did previously in the beginning of the video, of course you will start having shear, right? Okay. You mentioned this very briefly. How can I expand my knowledge on these types? How can you expand your knowledge on these types? Well, I did set up YouTube video being 18 plus, so just, I don't know, start taking shrooms and smoking weed, and then your mind is gonna expand anywhere you want it to be. But in reality, all jokes aside, practice, practice. Thermal expansion, for sure. That works. Trying to blow up a balloon also works. Okay, you will have a close vessel between the balloon surface and your and your mouth cavity. Okay, please don't take my advice on the shrooms. I did not know. Okay, fine. Okay, let's take a look at another uh, problem with the same thing, but this time is can it. I will guarantee you that it's gonna be a thin wall, and it will be a closed vessel. So this time we have a semi sphere. Sigma tangential came up to be 38.82 megapascal on the previous problem. Um, I actually should probably put it here. Free body diagram. Sphere. Sphere. Looks like a pill from a Dr. Mario video game. Okay, and I purposely drew it kind of with the thick lines just to accommodate for that thickness of the wall, just to say that it's thin walled, because it's just gonna take a lot more space for me to draw it out by hand. Okay, what do we have? We have both of the radiuses, actually both of the diameters will be 0.5 meters. The length is 1 meter and a thickness is 1 millimeter. Do I have to explain why it's a thin wall? We're comparing millimeters to meters. Okay, it is obviously way smaller than a tenth. Yes, it is a total coincidence that sigma radial was equal and opposite to the internal pressure. That is 100% coincidence. Don't trip about that. It is just the way how the numbers came out due to dimensions exactly. Um, let's see. Thin wall, right? What do we like about thin walls? Well, we definitely get one of the pressures being 0, and this time it will be radial, not pressure. Jesus Christ, it will be stress. Sigma of radial is equals to 0. Okay, and the others are a lot easier to calculate. Instead of going through all of that number of all of that nonsense of a lot of variables, you just go sigma tangential is equals to pressure times the radius over the thickness, and pressure axial is equals to pressure times the radius over double the thickness. Whoever just dropped it in the chat, thank you very much. Those are the equations that we are gonna go by. Now, how does this affect me in my calculations for a problem for my for Morse? Well, let's say I'm gonna draw another one of those segments right here. It pushed me being banned from the YouTube on the first day of me making an account. This guy advertises drugs. Ban him out. So this guy would be a sigma axial. This guy would be sigma tangential, and then this guy would be sigma radial. And sigma radial is just a 0 in our case. So, but when we draw this out, we'll literally cut out that square from the vessel and draw it out somewhere among these lines, where we have sigma A right here, and then sigma T right here. Okay? And this is actually a cool representation of why the position of them doesn't really matter, because I'm pretty sure if I will get my sigma T being bigger than my sigma A, my sigma 1 would equal to my sigma T. And then my sigma A would become my sigma 2. Especially if sigma A is gonna come out to be, it's not gonna come out to be negative actually, but oh well. If it would come out to be negative, I would just have to imagine that for it to be a positive, I would just flip arrows opposite way, and it will be in compression as opposed to tension. So sigma T is equals to pressure, which is 150 psi, times the radius was 0.25 meters. Which I'm just gonna right off the bat say that it's 100 centimeters per 1 meter, and then actually it's even better, it'd be 1,000 millimeters per 1 meter, which is 1 inch per 25.4 millimeters on this side. And then the same thing will be happening right here. The thickness will be 1 millimeters, which is 1 per 25.4 millimeters per 1 inch. Plug all that into your calculator. Then divide that by 1 over 25.4. Gives me 37,500 psi this way, and then sigma A is PR over double T, which is ironically enough would be just sigma T over 2, which is 37,500 psi over 2, which is 18,750 psi. That's nice. That's cool. And if I drop it on my Morse circle, Jesus, this thing really hates me. Now we'll just allow myself to be a little bit sloppy in terms of actual proper placing. I just know that sigma A is positive and it's closer to the origin than sigma T. It is getting late. I'll just say that this is the circle where this is sigma A and this is sigma T. And then sigma 1 is equals to sigma T, just like I predicted it would be 37,500 psi. And then sigma 2 is equals to sigma A is equals to 18,750 psi. I know that there are solutions online, and the solutions online give you answers in pascals, but it was easier for me, guy being born in Russia and raised in Russia, to find a shortcut and convert length units to, as opposed to convert a pressure units. They didn't specify exactly which way to do it. I just did it the way how I felt it the most amusing to me to do it. That's about it. Okay, we are 2 hours and 43 minutes in. How are you guys holding up? Wow, 2 hours and 43 minutes more. Guys, do you wanna, you guys are morbid. And add thumbs up on top of that. I'm a diehard. That was 80s. Are you that old? Really? I need the engineering money. The bank did all the work. I love it. How am I feeling? Uh, People keep saying that Bang did all the work. Bang really did all the work for me. Do I need a break? Oh, actually, as a matter of fact, I got to the point where I've covered everything as much as I was gonna prepare to cover in the first place. I think this has touched the surface upon everything. Um, how do you guys feel about those indeterminate equations when you have too many the forces? You don't think you won't go over deflection? Fuck it. Let's go over deflection. Um, I know we had that one problem, right? Determine reactions in EFL. We did that. Determine location X being where angle of deflection is 0 using singularity function. You guys can do that easy. Didn't take much time. It's actually BP3. Like BP for homework 10. Yeah, yeah. BP. Determine location of the mounted. They're they're both chunky boys. I'll go with BP3 just just because. Okay, because I covered for this already, I assume you guys are capable of finding all the resultant of forces, right? Right? Awesome. Let's go. Um, Starting off with a free body diagram. Uh, Supported, simply supported, 2 meters, redundantly supported at I third, and carries distributed load of sweet. Love those. Let's go. 4, 8, 12, just to make it easy. So that's my distributed. Erases it. And then that's the beam. Simply supported right here. Supported right here, and redundantly supported at 1/3. Purposely divided it like this. This is 1/3, and we have a distributed load all over it. If you guys remember on the lecture, he said, please use singularity functions because I know you guys gonna be cheating and looking for the answers online via free body diagrams and equations of through the static equation. I think he actually meant to say that get used to the singularity functions because that's how you guys kind of have to code it in the first place, especially if you're gonna start taking labs. You will have to use singularity functions in a MATLAB and use singularity functions in Excel if that is an option. I haven't found that out yet, but pretty much get used to them. So let's see, what do we have? We have R1, we have R2, and we have R3. Did we do BP2 earlier? I don't remember. No, we did only BP1 earlier. We didn't do BP2. BP2 would be pretty much the same thing, except you would just be looking for a place where the sigma x will be 0 and find the deflection in that. Okay. Q of x. Because this guy is supported at both ends, honestly, it doesn't matter where you make your axles go. I just realized that I need to put my frame of reference here. Please put a frame of reference on your work just to make yourself make your life easier for yourself. Y and extra here. So what do we have? We have negative distributed load of x minus 0 to the 0. Whoever is not muted, please mute. Thank you. Plus R1 x minus 0 to the negative 1 plus R2 x minus L over 3 to the negative 1 plus R3 x minus L to the negative 1. V of x equals to negative omega x minus 0 to the 1 plus R1 x minus 0 to the 0 plus R2 x minus L over 3 0 plus R3 x minus L to the 0 plus C1. C1 is what? I was actually hoping for like hands tossed down on a keyboard and just 0, 0, 0, 0, 0, 0, 0, 0. There we go. Good. Reason why? Okay, well, because law is not always is really not the answer either. Because L plus, okay. Because there are no other forces resultant being applied on a beam besides those that are already in the equation. Going on, moment of x is equals to negative omega over 2x minus 0 squared plus r1 x minus 0 1 plus r2 x minus l over 3 1 plus r3 x minus l to the 1 plus c2, which is also 0. And then what do we get? If I integrate this again, I'm gonna substitute for the moment in my head right over the bat, and gonna see it's a ei sigma x is equals to negative omega over 6 x minus 0 cube plus r1 over 2 x minus 0 square plus r2 over 2 x minus l over 3 square plus r3 over 2 x minus l squared plus c3, which is may or may not equal to 0. I will guarantee you that it's not gonna equal to 0 because I don't know where. I mean, it will be 0 at some point for the sigma being 0, but I cannot get rid of C3 because I don't know if it will be 0 or if it will not be 0 because it is simply a supported beam. There are no moments that are preventing me from the bending. So I have to integrate again. Say that I get ei y of x equals to negative omega over 24 x minus 0 to the power of 4 plus r1 over 6 x minus 0 cube plus r2 over 6 x minus l over 3 cube plus r3 over 6 x minus l cube plus c3x plus c4. Now what can we say about a c4? We know that y of 0 equals to y of l over 3 is equals to y of l. That equals to 0. And if it's like a game with a 3 lives. You got of 3 ammos. I'm gonna use it up once and say because of this guy, my c4 equals to 0. Okay, and then to find my c3, I'm gonna use l over 3. I'm gonna say that 0 is equals to negative omega over 24 l over 3 to the power of 4 plus r1 over 6 l over 3 to the power of 3. That's 0 plus c3 times l over 3, which can get simplified. That can get crossed out, that turns to square, that turns to cube. And we get c3 equals to move stuff around and distribute as much as possible will be omega l cube 24 times 3 cube will be 648 and then minus R1 over, I think it was 54. 6 times 3 squared will be 54. And then this is L squared. And now I might as well use up L as well to find what my R1 will be in this case. Let's see. 0 is equals to negative omega over 24 L to the fourth plus R1 over 6 times oops, L to the, oh, wait a second, this is not gonna really help me out in any good way, will it? Oh well, it kind of will eventually. It doesn't really matter which way we go. It will help out anyway, because I just remember that there is a lot more bitter process to this problem than ever before. That's why it took so long. Oh, spoiler alert. 2L over 3. That's a 0. Omega L cube over 648 minus R1 L squared over 54 L, just L. So I might as well actually distribute L inside and say this would be 4 in the cube. Okay. And what I can do is actually I can start rewriting equations of in terms of their equations, and the first things first, I do have to simplify by L cube. Simplify this, this, and this. Can we see the free body diagram again? Yes, this is a free body diagram. Okay. What if we cancel out exponents in the slope equation when I didn't? Solving for C3, I actually kept it as a C3, and then I integrated it again, and I got C3x. So I used y of 0 to prove that C4 is a 0. Then I used y of L3. That came out to be L over, that should be L to the fourth. That, oh my god, I just did a rude mistake. So yeah, I just did the big dumb mistake. Don't do what I do, even though I'm the one doing it. Yeah, the C3, I kind of goofed on it. So what I got excited about, actually no, I did it right. So what did I do it? I used the previous equation. Okay, I thought you were, no, I did use the deflection, and the reason why I simplified is because each and every term has L over 3 in it. So I actually canceled out L over 3 entirely through this whole thing. Okay. Yes, I factor out L over 3 and I divided by it. Right. Uh, where was I? Yes. 0 was also equals to negative omega over 24 L to the 4 plus R1 over 6 times L cubed plus R2 over 6 times 2L over 3 cube plus R3 will be 0. Right. And then here we have omega L3 over 648 minus R1 L squared over 54. And since I don't want to multiply by L individually, I might as well distribute L right off the bat. I'll get L to the fourth and L cubed right here. Okay, the only thing that I have to do is, honestly, so I would not make stupid mistakes, is to work with this term real quick. I'll get negative omega L to the fourth over 24 plus R1 L3 over 6 plus 8 R2 L cubed over 6 times 3 to the power of 3 will be 162 plus omega L to the fourth over 648 minus R1 L3 over 54. And now I can cross out a lot of L cubes, right? Because I can cross this out. I thought I changed the color. I can cross this out, this out, this out, and that's just WL and WL. And if I will make my life easier by combining like terms, get negative 13 omega L over 324. And then plus R1 over plus 4R1 over 27 plus 8 R2 over 162. And that will allow me to say that my R2 is equals to 162 over 8 multiplied by 13 omega L over 324 minus 4R1 over 162. And just to make this a bit less messy, 162 over 8 will be 13/16 omega L. And I believe this should be 1/2. I'm just gonna double check because it does get late, and when it gets late I get to carry it away. Yes, minus 1/2 R1. And now I get to rewind all. Can I zoom out screen when downstairs? Even zooming out is not gonna help to see this problem, because there's a lot more to come. Because now I gotta jump and loop back all the way to my shear and to my moment to accommodate for other things. Yes. So we get 0 is equals to negative omega. So we know for sure that shear at L plus is equals to 0. So we get omega L, negative omega L, plus R1 plus R2, which is 13/16 omega L minus 1 half R1 plus R3, which allows me now to solve for the R3 in this case. So get R3 being 1 minus 13/16 gives me 3/16 omega L. And then this would be 1 half minus 1 will be another negative 1 half R1. So now we can go to the moment equations. Say that moment at L plus that equals to 0 is going to be negative omega L squared over 2 plus R1 L plus R2, which is 13/16 omega L minus 1 half R1 times L over 3. Actually, it's 3, 2/3. They're taking a moment left to right. Yeah, so I'll be to the right of the beam, which is right in this area. It'll be just a little bit of a pass where the delta L is approximately 0, but it's also far enough for me to, say that it's kind of on the edge, but a little bit past that. So if I plug in L, that's L, 2/3. That's what I messed on. Should be 2L over 3. R3 is just a 0. So I can simply solve for the R1 in this case. Be 0 minus omega L squared over 2 plus R1 L plus 13/16 13 26 over 48. If I distribute that, omega L squared minus 1/3 R1 L. And if I move that on that side, 26 over 48 minus, is that 62? If I move everything on that side, it will be 1 half minus 26 over 48. Why does everything have to be so complicated? 24. So it'll be negative 2 over 48 omega L squared is equals to 2/3 R1 L. Cancels out, cancels out. 2 and 2 can also cancel out. Therefore, R1 is going to be a negative 3 over 48 omega L, which is 1/16 if I'm not mistaken. Now, because I got negative number, I thought that's what it's supposed to be. Let me just double check that. And then RA should be actually 1 over 24. I got no negative numbers whatsoever. I made a boo-boo somewhere. R2. Yeah, I'm just trying to accommodate for. I think I goofed on R2 right off the bat because I got 3/16, but then I don't have what I need to have for R1. So let me just look over that real quick again. How do you get there in the first place? We canceled all those out. We got. I think you carry the negative when you moved it to the other side of the. I could, really possibly could. You mean right here? No, the bottom one. The one that I was on right here. No, that is not the case because I just compared my R2 to the RB that I did over the homework, and that's why this problem took me quite some time to solve. Let's see. 1 over 24L 6L cubed 8 6 times 27 is 162. What was C3? Minus 12. So did I calculate C3 wrong? No, so C3 was right. C3, at least C3 was right. WL fourth minus 12 RAL squared over CS, so that's right. So I just made a mistake by doing L. Negative 6. Cube 2/3, so 8 RA2 642. Let's see. -3 R1. So that is what I'm thinking too. It should be -3 R1, and that is exactly what I'm trying to check right now. So negative 13. Okay, that comes out to be right. 1/6 minus 1/54. 4/7. That comes out right as well. 8. See, for some reason, for some reason, how does that change when if I combine R1s? Oh, pfft, thank you. There we go. There it is. There it is. See, a second pairwise that you will never be able to get on exam. Yes, that comes out to be my desired 3, which I'm gonna change right here. So this comes out to be plus 2. So then this comes out to be plus 4/3. So then this whole line is an A. So then I get 7/3 R1 because I can cross out this, and this. Then I get negative 1/2 plus 26/48, which comes up to be 0 negative 2/48 omega L. That's plus right here. 24. Yeah. Yep. Therefore, R1 is equals to 3/7 times 2/48 omega L. So that's 6 divided by 7 times 48. That comes out to be 1/56 omega L. Wow, I still didn't get what I wanted to get. My main question to you guys: do you get what's supposed to be done in the first place, or not? Yeah, like the general procedure. Yes, procedure. Find constants, then reactions back to equilibrium. Right. So then you just gonna use all the givens to find all your uh, data points, essentially. I just got lost at the constants. Uh, hmm. Where did I do a mistake again? Where's my R3? 2 array plus 3/16. 2R1 plus 3/16. Right. So that comes out right. Oh, I found my mistake. My R3 is 0. This guy should be 13/16 omega L minus 3 R1, because this is R2, not R3. I believe I'm gonna call this one being my last one, because the last thing I want to do is to set you up for the failure, guys. So let me write this down and solve this real quick. And yes, 0 would equals to negative omega L squared over 2 plus R1 L plus 26 over 48 omega L squared minus 2 RL1, where L squared, L, and L squared go away. We get, if I multiply that by 24, we get 0 is equals to 20, we get 2 over 48 omega L minus R1. Therefore, R1 is equals to omega L over 24, and I believe that's what R1 came out to be. Yep. Then R2 is equals to 13/16 omega L minus 3 omega L over 24. You get 11/16 omega L. And then R3 would be 16 plus 2 over 24. Then we get 13/48. Yeah, 13/48. So now that you know with those guys, we can find out deflection, because everything is essentially given to us. Okay, let's write this down again. EI of y times y of x is equals to R1. Actually is equals to negative omega L to the 4th over 24 plus 1 over 6 times R1, which is omega L over 24 times x minus 0 to the third plus 1 over 6 times 11/16 omega L. X minus L over 3 cube plus 1 over 6 times 13 over 48 omega L x minus L to the third plus C3, which was omega L to the fourth over 648 minus omega L over 24 times L cube over 54. X. And then you get to plug in two Torsion here. A lot of stuff will cancel. We get EI y of 2L over 3 is equals to negative, I forgot to say that this is x minus 0 to the fourth plus omega L to the fourth over 24 times 2L over 3 to the fourth plus 1 over 6 omega L over 24 times 2L over 3 cube plus 1 over 6 11/16 omega L over 3 cube plus omega L to the fourth hold up, cube and squared. That's what good stuff. $648 cube minus omega L cube over 24 times 54 to the 2L over 3. You have all the constants and every given infinite inertia can be found because we know that this is a simply supported beam with a diameter of 25 millimeter. You can find inertia being pi over 64, I believe, 25 millimeters to the fourth. E can be found in a book. Since this was a steel, I believe it's 206.8. Yeah, 206.8. megapascal. And just plug in this whole thing into the calculator, and you should be getting something along the lines such as y of 2L over 3 equals to negative 142.7 millimeters. Okay, are there any questions about this? That one was fat, I know. That's why I was like, you guys asking. I'm like, hmm. Yes, exactly. Inertia is equals to pi over 64 times diameter to the fourth. Yes. I believe the problem says that it is the diameter. Yes. Uh, beam is made of steel, has the diameter of 25 millimeters. Right. Okay. Any questions so far? Going back to the problem. Okay, I think this is a great place to stop recording. As I am gonna stop.